So I'd like to go through an example of linear regression and the interpretation of the slope and y-intercept and r squared and a residual plot and how all that works. And so here's the example I have. It's the number of hours that a business spends in safety training and the number of hours lost due to accidents. And so if you need to pause the video at any point, do that. But first we want to enter the data into the calculator. And so in my TI, I've gone to my list, so stat, edit, and type this information in. And the first thing it says to do is to draw a scatter plot. That's always a great idea to start out with a picture in your mind of what it looks like. So I'll go to stat plot, hit enter, make sure my first stat plot is on, and then I've got a scatter plot of L1 and L2. To graph it, press zoom 9. And you see my line is already on there. Let me take that off. So here's what it's going to look like. It's convenient when you can do it this way. And then I of course need to put a scale and a label and a title on there. And so I know that down here I have hours trained, and over here I have hours lost. And this is safety training. Whoop, I'm having a hard time with that. Safety training. And I should put the scale on here so that I see this goes from 10 to 80. So this is something like 10 to 80, and the other one is going to go also from 10 to 80, it looks like. So maybe I'll put 0 to 80 or 0 to 90, something like that, so you can get an idea of the magnitude of the numbers on here. And then it says, what do you notice? So there's really 4 things I'm looking for here. I'm looking for the strength, the form, and the direction, and then I want you to put it in context. So it appears that I've got a linear relationship that's in a negative association, and the association seems to be fairly strong. So I'm going to say there is a strong negative linear relationship, and then put it in context between hours trained and hours lost. So continuing, it says now let's find the slope of the LSRL and interpret it in context. Now this particular problem didn't tell me to do this, but I could remember that the slope is given by this formula. So if I need to, I can show the work for that, and likewise I'll go ahead and write down the formula for the y-intercept. It's A equals y bar minus b x bar. Well, that's not working right there. There we go. But for this problem, I'm just going to use the calculator to do it. So on my home screen, I press Stat, Calc, and I'm going to use number 8, linreg a plus bx. I like this method better myself, so I'm going with a plus bx. Number 4 will give you correct answers as well. So I hit enter, and while I'm here, I'm going to put y1 right here to store that regression equation. So it's vars, y-vars, function, y1, and that puts that y1 there. Now when I hit calculate, it gives me all this information. I'll just drag it over there for right now. If the r and r squared don't show up, then I can go to my catalog, scroll down to the d's, so I press D, go down here to the diagnostics on, hit enter a couple of times, and then I could repeat that process, and it will give me the r and the r squared that time. I notice when I do it, it also stored the equation right here into y1. So looking right here, the question was, what is the slope? And I don't really want to put all this information down here because then it looks like I don't know which one the slope is. So the slope is this one right here. And then it says interpret it in context. So what that means is every time x goes up by 1, we expect y to change by that much. So I'll say here, for each additional x, now x was hours trained, I expect to see a decrease because it was negative, of 1.066 hours lost. And I put those in green so you can see what's going on there. I also wrote I expect because I know the line is not perfect, so it's not going to always work out exactly this way, but that's the general trend that I could see. Now the y-intercept is going to be this value, that a, so the y-intercept is negative 92.057. Sorry, not negative 92, 92.057. And what that means is when x is 0, I expect about that much y. So again, when x was hours trained, is 0, I expect to see 92.057 hours lost. And you could change the grammar on that a little bit to make it say something like, if we don't do any training at all, we would expect to see about 92 hours lost. And a little rounding in there is fine, as long as I have all the data still saved with all of its digits somewhere else. Number 4 says report the LSRL and be sure to define your terms. So what that means is this, right? Y hat equals 92.057 minus 1.066x, where x equals hours trained and y equals hours lost. The hat's important because it tells me it's a guess or an estimate, and defining your x and y is also important. Alternatively, you could write hours lost hat equals 92.057 minus 1.066 hours trained. So now I've put the terms of the variable right there in the equation, and I wouldn't have to define an x and a y. Continuing, it says what is the correlation coefficient, and that was written on this sheet as well. I'll copy this over here, copy it, paste it. All right, the correlation coefficient, sometimes just called the correlation, and that is R. So R equals negative 0.95296. And what that means is if I treat the data as linear, the points are pretty close to that line. So if I treat it as linear, the points are close to a negative linear relationship between hours trained and hours lost. Again, putting it in context. That doesn't necessarily mean the data are linear, but if I treat them as linear, that relationship is really strong because R is really close to -1. The coefficient of determination is R squared, and so R squared is always non-negative. In this case, it's 0.908. And this is kind of hard to understand sometimes, so I would just encourage you to remember a cookie cutter statement like this. 90.8% of the change in Y can be explained by the LSRL of Y on X. And then I don't really want to write of Y and on Y and X. I want to put that in context. So now I'm going to go back and get rid of that y and write hours lost, hours lost, hours trained. So 90.8% of the variation in hours lost can be explained by the least squared regression line of hours lost on hours trained. That's what R squared is telling me. It's a percentage. R is not a percentage. R squared is. Draw a residual plot. So a residual plot tells me the points that are left over. The difference, if I graph this, it's the difference between the points in the line each time. And so one way to do a residual plot is to change this L2 to resids. So press second list and go down to the one that says resid. Now that's only done if you've done linear regression. So you have to have done linear regression first. So now my graph is L1 in resid. I press zoom 9 and I get this graph. This is a residual plot. So this here I've graphed hours trained, and here I've graphed my resids or my residuals. And I could look at a size here if I press window. I notice this line going through here. Ignore that line because that line is just that line, which is actually inappropriate for this graph itself. So just ignore it. Luckily I drug it over before that happened. Press window and I see that my x's of course are in that same interval they were before, from 0 to 80 or 10 to 80 or 0 to 90, and then my y's look like they go from maybe negative 20 to 20. The window's a little smaller than that, so that's a good enough look. And what I'm looking for in this is a pattern, because this tells me what data was left when I take out the pattern of the LSRL. And I don't really see much of a pattern here, so that tells me that the LSRL was the best method. Since there is no pattern in the residual plot, the LSRL was the best method to use. So if there had been a pattern there, then the LSRL wouldn't be the best way to go. I should use some sort of curved function of some sort. Now I also think it would be good perhaps to see this. So let me move this stuff here over. And then I'm going to show you one other thing. If I go back and make my regular graph, so L1 and L2, and I hit zoom 9, and I see this line on here, and I'm going to drag this down here. Now what I want you to see is if I rotate this so that this line here is now horizontal, what I've got is essentially a zoomed in version. When I look at this, it's the same thing as this, because that's what a residual plot is doing. See, I have a couple points below the line, a couple points below the line, above, above. It's the same idea. That's what a residual plot does. Now at other times you might see the horizontal axis here done differently. Sometimes people put the Y or even the Y hats on this horizontal axis. It's all fine. I'm still looking for a pattern, the same idea. And if I don't see a pattern, then the method I used was the appropriate one. If I do see a pattern, then the method I used wasn't the best. So just be careful that you read what's on here if you're reading somebody else's graph. Number 8, what does the LSRL predict for hours lost when trained hours is 35? So on my calculator, here's one way to do it. What I really want to do is plug a 35 into this equation, and here's an easy way to do it. Vars, y vars, function y1 of 35, just like we do in f of x. I plug that in right there. That's what it predicts. Or when it's 100, vars, y vars, function y1, I can plug 100 in there. There are my two predictions. And then it says, how close do you think your answers will be to the actual value? Well, the 35, I think, will be pretty close because the line did a pretty good job. It was the best method, and my R and R squared were pretty impressive. So I think this one is good. I like this guess because my line was appropriate and the R squared is pretty good. Now this one seems funny to me, and it seems funny to me because it's negative, so that means people are actually going to work more. But the reason that it's problematic is this is extrapolation. The 100 is outside the domain of my x's, and my trend is uncertain out there. Since the 100 is outside the domain of my x's, which is called extrapolation, the trend there is uncertain, and the prediction is unreliable. So that's a pretty good way to look at a regression line, the residual plot, and the various parts of that interpreted in context.